Our project focuses on recommendation models and specifically benchmarking wide and deep and cross neural networks models. So, why recommendation systems? These days, people use a lot of online services like YouTube, Spotify, TikTok, Amazon, and Netflix. And as an online service provider, in order to create the best experience for your customer, you would want to figure out their interests and what sort of products they may be more interested in. So that requires you having a robust and accurate recommendation engine that could predict that could exploit item and user metadata or interaction of users with your systems in order to predict products and figure out what sort of items your user may be most interested in, and then you could recommend those items to the user. In terms of background work in recommendation systems, there have been various approaches. The first one is wide and deep learning for recommender systems, which was an early attempt for recommendation systems based on deep learning. And they proposed a model to jointly train wide and deep components for recommendations. The next model is called DeepFM, which is a factorization machine-based neural network for CTR prediction. So this approach proposed an end-to-end model without needing to pre-process data, and they shared inputs between two wide and deep components. The next approach, which is also what we sort of focused on, is a deep and cross network for ad application predictions. And this proposed an efficient model that allows for feature crossing up to a desired degree without needing feature engineering. And the last work is deep learning recommendation model for personalization and recommendation systems. And they propose a state-of-the-art model that can be effectively trained in parallel while still having improved accuracy. So about the technical challenges, there are quite a few technical challenges when it comes to recommendation systems. First of all, the applications are really diverse, and the data types and feature types are also different. As an example, the data that you may gather from a platform like Amazon could be pretty much very different from the data that you gather from a platform like Spotify. In terms of the type of the data or the type of the product or the type of interaction that even users have with your platform. There's a lot of like various aspects you need to think about, and so this makes it hard to come up with a generalized solution for an application. Another problem is called the cold start problem, which is pretty much common, and it's basically the beginning of your training the neural network for the recommendation task. And because your data set or your model is pretty sparse, maybe you're gathering maybe you're working on a matrix factorization technique, and your matrices is really sparse. Therefore, you do not have even much data to initiate the prediction, and so your predictions are pretty much poor. So this is a common problem in recommendation systems, and there are approaches that you could deal with the cold start problem in general. Other technical challenges, which is specifically on our case, is that there are tons of categorical data, which is really painful when working with TensorFlow because you need to do a lot of data pre-processing. Also, the task of recommendation is relatively new, and there isn't like a really widespread documentation on these recommendation systems. So if you're someone who doesn't have much knowledge in deep learning or even specific technical details of recommendation systems, there isn't much you can do in order to like use a recommendation platform, because even the simple models are quite complicated to work with. And there are also limited compute resources, which could basically make trouble when training on different platforms. So our approach, basically the data set is that we proposed to focus on one of them were the Netflix data set, which consisted of movie and show reviews by Netflix users. We intended to use this as an input for our model, but we decided not to use this data set because of the lacking metadata based on our chosen architecture, because the Netflix data set only had interactions between users and movies and ratings. We did not find it a good fit as we went along the project to use that for our model. But the next one is the Movie Lens dataset, which consists of movie reviews by users in addition to metadata on users. And this is a very common data set, when evaluating recommendation models. So it includes metadata and features about users, like age, occupation, zip code. In terms of our approach, in terms of the evaluation metrics that we considered, we wanted to look at a variety of different metrics that might be valuable to know, like training time, RSME, improvements with more epochs, performance with extra layers, qualitative analysis, and the overall performance between two models. And this led us to think of the following experiments, of which we decided to test with 4 configurations. So we sort of checked RSME versus total units. We checked RMSE versus model complexity in terms of number of layers. And we worked on training time versus total units, and then RMSE versus epochs. So now I hand over to my teammate Brian to continue with describing the model architecture. Thank you.
All right, so here are the 2 models that we're working with for our project. We have the wide and deep model on the left and the deep and cross model on the right. And what's really important to know about these 2 models is that both of them have a deep component or a deep network as a part of their model. And that the output from that deep component is combined with, in the case of the wide and deep, you can see the cross product transformation, and in the case of the deep and cross, you have the cross network. Basically, what these 2 components are trying to do is they're trying to model feature interactions between your categorical features, which is something that tends to come up a lot in recommendation systems. And kind of the big reason that we're comparing these 2 models specifically is that they have this similar architecture of having a deep component and a specific kind of bespoke component meant to model feature interactions. So moving on to our implementation details, we were kind of very specific about wanting to be able to compare between the 2 models rigorously. And so what we did is that we made sure to implement both using TensorFlow. And because of that, there wouldn't be any discrepancies between frameworks that might alter the performance between the 2 models. Additionally, moving on, we used Google Colab initially to train our models using a K80 GPU. But we quickly ran into usage limits. And because of that, we eventually had to use a Jupyter Notebook server on a GCP compute virtual machine using the same GPU. And we ended up having to open it up to external traffic via the firewall rules, and then we could connect to it through our computers, allowing us to run the notebooks. Now, this situation right here kind of highlights one of the, biggest challenges that we faced, which was the memory and compute resources that we had access to, or lack thereof. Basically, because we didn't have, the best memory or really strong computers, we weren't able to use the entire data set. We ended up having to use a small subset of the data set that was representative of the bigger one. We had about 100,000 records. In the future, if we were to extend this, we would want to train it on the full data set, and additionally, maybe even use different types of hardware because performance might have been altered based on what hardware we're using as well. With that said, we've prepared a demo. So here we have our demo notebook. You'll see that we trained both the deep and cross model as well as the wide and deep model for about 10 epochs just for the purposes of this demonstration. And with those models trained, we basically, made these predictions and took or made predictions on the test data set and took just 5 random representative um, records from the data and just wanted to take a look at that. So right here, and let's refresh the data frame. So a couple things to note. Sometimes the model gets things really right. In this case, you could see that the predictions of a rating of 4.5 for both of the models is pretty close to the actual rating, which is 4.0, as well as the one below it. But sometimes the models don't perform that well. So on the top, we have these predictions, which are actually pretty far from the actual ratings. And then even there's this little outlier right here where the deep cross network ended up predicting a 0, which is very bizarre. One thing we thought that was also kind of interesting from this demonstration is that some of these records kind of make sense, and that's kind of why we picked this sample specifically. Like, it kind of makes sense that, a 45-year-old librarian would be interested in Schindler's List, which is, a very historic, kind of critically acclaimed film. And yeah, it's kind of cool to see that the models are picking up on that. So moving into some of the results from our experimentation, we have these 4 graphs. On the left, we have experimentation with changing the total number of units between the 2 models, specifically on the deep components for both of them. And on the right, we experimented with changing the number of hidden layers, the depth of these deep components. And something that we thought was particularly interesting was that the deep and cross model is being outperformed by the wide and deep initially with respect to the total units. But over time, the deep and cross model gets better, or I guess the wide and deep gets worse. One thing that we did note was that the wide and deep model seems to be outperforming the deep and cross model just generally with respect to the RMSE. So here are just the general results between the 2 models. Basically, we experimented with training the models for 25 epochs, 50, 75, and 100. And you can see that the wide and deep model is always outperforming the deep and cross model with respect to this case. It's also worth noting that all of these are with respect to the test data set. So it's not the training RMSE. But that kind of leads to our conclusion. In conclusion, first of all, more generally, recommendation systems are everywhere. And they're used by so many different companies and so many different content platforms, and they drive so much business value. A lot of these companies, they make money off of advertising revenue, and so they are incentivized to keep people on their platforms. One thing we noticed from our experimentation and our project in general was that you need a lot of compute resources as well as a lot of memory to be able to train these robust models. And even if you don't have enough memory, you would need something like optimization with memory to get these things working. And that's kind of been a through line through our whole class where with respect to production, there are so many considerations that you need to make, and making efficient choices with respect to that is really necessary. It's especially shown by how we weren't able to train on the full movie lens data set. And while we think it's representative, we still can't make big conclusions, and that's unfortunate. And lastly, with respect to some of the results that we just saw, sometimes simpler models might outperform more complex models. And that's just something you need to get over by experimenting. And if there's anything that we've learned from this project, it's that experimenting is so important. And we've kind of learned this from all of our classes, but this is just consolidating that even further, where this simpler model is outperforming our more advanced one. And let's say even if this model didn't outperform it, it still acts as a baseline, and from there we can make comparisons and actually show how much of an improvement a more complex model would be. Either way, it kind of shows us how important experimentation is, and with respect to recommendation systems, it's no different. With that said, that's pretty much the end of our presentation. Thank you so much for listening. And we kind of had to go through this material pretty fast. So if there are any questions, feel free to email us and we'd be happy to answer.